Um, but okay, so last time we started talking about doing classification on continuous variables, okay? And we saw that continuous variables with this, they have the property that all the distinct values, like when you train, the distinct values are, sorry, the training data will have distinct X values. And so the technology that we had, this estimator, that does not work. So it produces like an interpolation, and the interpolation is not like not defined outside the training set. So we can't really use that to predict new data. So the idea was to use an approximation of it. So what you can do is there were some sort of proposals to, like, for example, round these and then count how many they are, and assigned a homework problem to try to do that. The general idea is to come up with a similarity measure, right? So find a similarity measure. This is like a similarity measure. So this is saying I'm going to average all yi's for which xi's are similar to my test case x. A similarity is with exactly the same x. So in the continuous case, we can't do that. Or rather, it's going to be really give you a trivial example. So what we can do instead is try to replace this. Let me maybe move on to the other set of slides. So we can try to replace that indicator. So it used to be like this: eta hat of x is equal to summation I from 1 to O. So we had eta hat of x is summation I from 1 to n, indicator xi equal x yi divided by summation I from 1 to n, indicator xi is equal to x. So what we can do is we can try to replace this with a more like a softer version of similarity. So I'm going to average yi's with a weight, which is the similarity of xi to x. Okay, so this x is my new test case, let's say. And the way that I define this could be very general. Okay, one idea that, like, I think Jing Tian mentioned is like, I'm going to round xi, I'm going to round x, and then compare them. If they're the same, they're similar otherwise. So that's one measure of similarity. The other idea was to say that, for example, if they're close, I'm going to say indicator. So idea one was the rounding. Idea two was like, okay, xi and x is like indicator if xi minus x is less than some epsilon, or I'm going to call it h because that's what we're going to use. So h I can pick, for example, I can pick 0.1, 0.5, or whatever. So this is a relaxation of, instead of saying exactly equal to x, I'm going to say the difference is small enough. So that's another idea. K nearest neighbor was another idea. So this could be like indicator that xi is among the k nearest neighbors of x. So you go in your data set. These are x's, for example, or let's say do it from the data here. So in nearest neighbor, what it does is, suppose I observe a new x here, or let's say I observe something here, right? Let's say tree nearest neighbor. I'm going to look at all my data. This is my new x. So this would be sometimes you could write it as like x1 of x, the closest one, and then the second closest one, maybe this is x2 of x, and this is like the third, x3 of x. So these are the three, and then I'm going to average y's over these. the average, sorry, average of y's of these coordinates. And then I'm going to be, that would be my regression function. So y hat x would be, sometimes you might write something like 1 over k summation 1 from 1 to k. Instead of the indicator, I'm going to say, okay, indicator. Yeah, hard to write, but you know, it's like, let's not do this. Just, yeah, these are going to be the candidate ones. This, and that. So I'm going to look at the y. Yeah, you have to call it something like y. This is y, this is yj, this is y. L, so I'm going to average these, like 1/3 of the sum. So in general, it's going to be like xi among k nearest neighbors of x. Okay, so that's another average, and this is actually an example of this. It's an example of this because if you verify, when you sum this and then denominator, it just would be k, because this is going to be exactly 1 for k of the xi's. So the denominator here would be this k. So it gives me the, in this case, it gives me what I want. So it gives me eta at x is summation I from 1 to n indicator. Exactly that, and then the denominator would be k, because I'm summing ones over k of them. So it's just averaging over yi's over the k nearest neighbors of x. So k nearest neighbors is an example of this with this kind of similarity measure. Okay, so you can say x is similar to xi if this holds. Sounds good? Questions? Does that make sense? So a great deal of interesting estimators can be written like this. Not a great deal, but this is a fairly general form. And then you can also view this as this. So summation, this is like a number. I'm gonna put it inside. It's like I from 1 to n. Let's call this, what should I call this? I don't know. D of x if you want. So this is gonna go inside xi, x, d of x, let's say, and then yi. And then I'm gonna call this w I of x. Okay, with this notation, these estimators can be written like that. And you can see all of them look like a weighted average. So I'm averaging yi's with a weight which depends on x for each sample, right? And you can verify this is just, if you sum this in this particular case, with this wi, the summation is actually going to be 1. Just verify it because the summation of the numerator is going to be just d of x. So it's like a weighted average, but the weights are local. That's what I'm calling it, local averaging or locally weighted estimators. Okay, so that's a fairly general class of estimators, right? Easy to calculate and actually performs really well, as we'll see. Questions? Is it clear how we got this? So you have to go back how we got this. And the way we got this was a very natural way of doing empirical estimation of the joint distribution. But because yi was like binary, that would correspond to that. So in our case, as you remember, this was probability of y, estimate of probability of y equal 1 given x is equal to x. That we came up with this from empirical averages. And then you can relax this. You can think of this as averaging either similarity measure, you can relax it to that. So if you understand where this comes from, it's a very natural estimator. Okay. Good. Questions? Okay, so a particular way of doing this is defining this k of capital X and X to be like this. So this works when like X is any vector in RD, because in RD I have translation. And so this is like taking a base, we'll call this kernel, K naught, and then translating it and scaling. So for example, if so can anyone tell me what kind of, so this is a way of defining it, the general kernel. So these are called kernels, like similarity measures. So for example, if I have like one choice is K naught being, let's say we are in the univariate case. Let's say X is in R. So K naught of, I'm going to call it T, is e to the negative, or u. It's like a dummy variable, e to the negative u squared over 2. So this is going to be like a Gaussian kernel, 0 here, and it goes down. So it's actually, yeah. So can anyone tell me what this would look like for a general little x and x? So this k of x and x would be like 1 over h e to the negative capital X minus x squared divided by 2 h squared. So when you plug that in, if you plug this for u, that's what it looked like. What it will look like. So something like x minus h squared over 2 h squared. So for different h and different x, little x, what would it look like?
Standard.
Sorry?
Standard.
Forget about that. This is normal. Like, okay, so like give me a function, general function. The fact that I just want to look what shape would it, so what does this do? What does this parameter do? Sorry, this is not h. This should be like x, capital X minus little x divided by, let me do it on the other page. Not enough room here. So if this is like that, then k capital X little x is going to be like 1 over h k naught capital X minus x divided by h. It's going to be 1 over h e to the negative x minus little x squared divided by 2h squared. Right, if I look at it as a function of x, so this is, I'm going to plot this as a function of this capital X. The notation is not perfect because it's confusing. But this is like R, this is for us like a training example. This is like a test. Capital 1 is like training, but both are in R. So what does this look like as a function of capital X if I fix little x? So if this is k naught, what would this look like? This is like a translation. Let's call this a k of x if you want. Capital X. This is like little x is 0, h is 1. This would be like x squared divided by 2. So this is x, this is k naught of capital X. Let me do z here to be not confusing. Z. Okay, this is a dummy variable. So now what does it look like for a general z? Let's say z is here as a function of x. So this is like maximized at 0. How about this? So this is like a translation and a scaling, right? For normal, it would be like changing the mean and the variance, right? If this was a density. So it doesn't seem to be familiar to people. So what this does is this just shifts this guy to here. So the center just moves to here, and then the scale would vary. So it could be like, this would be for h equal 1. For small h, it would just like be scaled. For larger h, it would be like flattened. So this is h less than 1. This is h bigger than 1. This is going to be h equal to 1. It just shifts and rescales the bump. Okay. Sorry, the other way around. It's going to be maximized here, but this is h less than 1. Sorry, this is okay, bigger than 1. This is h less than 1. The other, like, easier to see for like a box kernel. So this is called the box kernel. So if you have like a kernel that like -1 and 1, it's 1 here and 0 elsewhere. So let's say k naught of x, capital X, is indicator. I can write it as x less than or equal to 1. Okay, this is what it does. If x is less than or equal to 1 in absolute value, it's going to be 1, which is this. And otherwise, it's going to be 0. So it's like a box kernel. And if I form this capital X and Z, this is going to be 1. Again, it's like k naught, 1 over h, x minus z over h. This is going to be 1 over h times indicator x minus z divided by h less than 1. You see this is going to be similar to what was proposed. So if I multiply both sides, it's saying x minus z is less than or equal to h. Okay, so what is doing is that would be k naught of x. K naught of x z would look like, around z, so the center would be z. And if x minus z is less than or equal to h, so it's like z plus h, z minus h, it's going to be 1 divided like times 1 over h. So it's going to go, could be like, for example, 1 over h here, right? And then 0 elsewhere. So if h is very, so if h is small, then 1 over h is going to be large, and then this interval will be small. So it would look like this. It would look like that. If h, like h small, and it would be like this if h is big. Okay, this is h is big. Because if h is big, 1 over h is small. So it's going to flatten out and be extended, or it's going to be like peaked, and right, so you can choose how peaked it becomes and how like both the support and the, does that make sense to people? Sort of. So you can change the scale of it, right? And like this is the support basically, where it's non-zero. You may think of this as like 1. So it's going to be z plus minus 1, and the height would be 1. But if this is 10, it's going to be z plus minus 10, and the height would be 1 over 10. if this is like 1/10, it's like going to be z plus minus 1/10, but the height would be 10. Right? So just squeeze, like shoots up to infinity, like big, or like flattens out. Okay, so this is sometimes called the bandwidth, this edge, and you can see controls the spread of this function, right? And what happens is that when I form the estimator, so the estimator, what it does is, if you remember, it's going to be summation k. I'm going to plug it in here. So 1/h k naught xi minus x divided by h times yi divided by, that's the estimator that we had, 1/h k naught xi minus x divided by h. So these h's will cancel out. They don't matter. So what I get here is summation I from 1 to n k naught xi minus x divided by h. So I'm going to put one of these bumps around every one of these yi's, right? So one of these bumps, and then I'm going to add things up, right? So I would get something like, and then the bottom would be xi minus x divided by h. So for example, if this is like x1, x2, x3, x4, x5, and this is like, they're either 0 or 1. The y's are either 0 or 1. Could be y here, 1, and then 0 here. So this is yi, the y-axis. So I'm going to put a bump here, right? Let's say this is the Gaussian kernel. So bump here, right? The same height. And a bump here, the same height. And then I'm going to average. So because this gets multiplied by 0, this is not going to take an effect. So this is going to be basically times 0. So this is going to go away. This one is also going to go away because it's 0. These guys are going to be multiplied by 1. When I add them up, I would get like something which looks like this. Right. So now if my bandwidth was higher, so it would be like, this is still 0, but I'm going to have like something like this big here, and then another one here, and then another one here. So when I add them up, I would get like something which is like this, sort of. So that would be my eta hat. So this here would be close to 1. Elsewhere would be close to 0. And so I can like predict sort of things that are here, probability that they're from class 1 is 0. Otherwise, they're from 1. Does that make sense intuitively? There's like large bandwidth. They're just shifted and then anchored at these data points, x1 up to x, and then those are y's, right? So these are yi's. This is also yi's. So the ones that are 0 get multiplied by 0, so they go away. The ones that are 1s, they get multiplied by 1, and then you average out. There's this piece as well you have to take into account, but would look like this, or if the bandwidth is good, would look like that, which is a nice estimate of eta hat. Does that make sense? Sort of. Questions? So in any case, so if you think about this, let me know if it was questionable or not. But if you do it on this data with this guy, right? So these are the radius mean. Diagnosis is either like malignant, which is 1 or 0. Okay, benign is 0, this is 1. I'm gonna do it with the sorry, the other way around. 0, 0, 0, 1. Okay, these are yi's. I'm going to plug in the Gaussian kernel here. So I'm going to form, so this is sometimes called Nadaria-Watson. Nadaria-Watson estimator when you do this translation invariant. So this is called translation invariant kernel because I'm doing it by translation. Because I'm moving it like a base kernel. These are called kernels. Moving it to different positions by translation. So from a basic, like univariate function, you can build them up like a bivariate function. These bivariate functions are called kernels. So measure the similarity, but we use the base kernel. And this can be generalized. This can be generalized to multi-dimensional case. So this, for example, is like the case when U is in RD. Instead of like U squared, I'm going to take the norm, L2 norm. This box kernel, I'm going to take the L2 norm here as well, or you can take the L infinity, which we'll talk about maybe later. But there are other kernels, Panichnikov kernel, and so on. So there are other kernels that you can build. But let's work with Gaussian kernel, and you can call it uniform or box kernel. I gave you these two for the univariate case, but the general case is sort of similar. So you can translate this. Translation means I'm moving it to position X by translation. That operation X minus X is translation. And so you put these by translation, the same kernel, once you're scaling is by this bandwidth edge. So the bandwidth edge is called bandwidth. You can see it's like has something to do with the bandwidth. If it's like large, that it's like I'm extending the bandwidth of this. If it's small, actually, if it's large, it's going to be, this is large, this is small, like it's more, it's actually going to be more peaked, but because I'm normalizing it, it doesn't matter. So what we get is, so you get this estimator, let's say, which if I apply, let's say with the Gaussian kernel to this data, which is just a single variable here, I would get a plot like this. Okay, so this is, so this is the x-axis. So these are my x's, right? I don't have an axis, but you can see it goes from like maybe 8 or something to should be somewhere like 8 here, maybe 20 here. But there's a lot of data points like here, not much here or here. But then you can see there is a nice transition. So these curves are those Nadaria-Watson estimators. So how did they like compute it exactly like this? Okay, so you put a little bump around every point and then you add up y's. So if you just calculate this as an exercise, you're going to do this estimator. If you calculated it for the Gaussian kernel with bandwidth 1, 3, and 0.25, you would get these curves. So there is a green curve which is not easily visible. That's this for bandwidth 3. This is bandwidth 3. That would look like very smooth because the bandwidth of the Gaussians are pretty big. One is this black curve, and then the red bandwidth small, you can see, because of these bumps are getting shorter, when you add them up, you have this ripples, these ripples, right? And there's no logistic regression here. Okay, there's nothing, just this. And it produces these nice, so this is your estimate. This is your estimate of, for example, that bandwidth is your estimate of the regression function eta hat. So this is like eta hat. From Nadaria-Watson estimator with Gaussian kernel. Okay. So you can see like this is like 1. This is 0, and if I threshold it at 1/2, I can form my classifier. Remember the classifier that we had, that's our estimate of the Bayes rule would be like 1 if eta hat is bigger than 1/2, 0 if eta hat is less than 1/2. So depending on which bandwidth you choose, you might get a different thing, but this is like roughly like this is 0.2, 0.4, 0.6, 0.8. So somewhere here would be like 1/2. So this is saying you're going to cut this at different points. So this is going to be your decision boundary under this. So decision boundary here would be just a single point. This is going to be your decision boundary under the other one, right? So these are the decision boundaries. For this, it would be that. For the other one, it would be this, and for this one, it would be that. Right, so this position, basically. Anything under this green one, anything above that, if x is above that, you can see 8 of x bigger than 1/2. So you can classify anything above this as 1, classify anything below this as -1. You can see if you do this, you're going to classify the zeros on the training very well, but not all of a lot of the ones here, these are the ones in the training is going to get classified. Sorry, a lot of the zeros here. So if that's my classifier, if I do it like that, I'm going to classify a lot of these correctly because these are 0. And then I'm going to classify these correctly, but these are going to be classified as zeros. Right? You see, the training error would be large. So these are the training data. So I'm plotting xi. So this is like one training point. So this is their x, this is the yi. So this is another one whose x is exactly this, but the y's are 1. So you can see there is some overlap. You can like perfectly separate these by single thresholding at a single value. So we threshold here. All these training data points to this side are correct. This is misclassified. And all the things that are here are going to correctly classify. This is going to be misclassified. If I do the red one, the red is very close to, I'm going to classify at this point. So anything to the left of the red one would be classified as 0. Anything to the right would be the other way around, depending on which left or right. So anything here would classify as 0. Anything this side would be classified as 1, right? And you can see you're going to classify. So some of these will have more errors on the zeros, but less. So you're not classifying these parts correctly, right? But these are incorrect. These are incorrect, these two pieces, but the other parts are correct. So this and that are going to be misclassified. For the other case, this is going to be misclassified and these are going to be misclassified. So there's like a trade-off here. And for the red one, for the black one, you can see it's like very close, right? So there is an effect of this bandwidth. And there are a lot that you can learn from this plot. Let me pause and see if you guys have any questions. Okay, these shapes we didn't like cook up. It just came up because of the data, right? I did not assume that like eta hat has to have this form. But if you apply that classifier that we like naturally constructed, then it would look like this. The eta hat would look like that. And in the green one and the black one look like something that you might be familiar with. The red one is like has more ripple. Okay. Questions? Does this make sense to people? This is a very easy classifier, right? There's nothing that you need to do in training, basically, except choosing this edge. And we'll talk about choosing that edge. But once you choose edge, there's no training, basically. 0 training except choosing the bandwidth edge. Once you have it, it's just at the test time. At the test time, you're going to plug in x, and you can calculate this, and it gives you the eta hat x, and then you can threshold it, figure out. But it gives you more information, actually. It gives you all this. This is basically the probability. So remember, p hat, this is eta hat of x is really p hat of y given x is equal to x. So it's outputting for this one, for example, under the green, the probability is like 0.8. under the other one is also close to 0.8. But this gives you a very nice way, and you can generalize. This is easily generalizable to multiple dimensions. So this Nadarya-Watson estimator is a pretty cool estimator. We didn't assume much. So I didn't assume a parametric form. We'll see later about the nature of the data. And there's not much training except figuring out the bandwidth. And you can see there is some sensitivity to bandwidth. There's not very high sensitivity, as we'll see. But let me ask you if you have questions. Is this clear? Is this picture clear? Clear, not clear. If you do some homework problems, become more clear. Okay. So one thing to note is, so the smaller the bandwidth gets, the more ripples this is going to have. And this is sort of like indicative of something which is called bias variance trade-off. So the ripples are not exactly related to the variance, but it's just a manifestation of the fact that this estimator will have higher variance. It's just manifested like that. The ones that with a smaller bandwidth, they have smaller variance, but they'll have higher bias. So there's a trade-off as you vary this edge, you're trading off bias for the variance. And I'm going to maybe talk a little bit about that, or maybe a lot about that. Yes.
I was just thinking, what if what is the cutoff point landed at one of the local maximum?
Sorry, what is the
0.5 cutoff point?
Yes.
Or the small bandwidth? What if it then on one of the local maximum point?
Right.
So when it goes like when I go from left to right.
Yeah, great.
It started like decreasing, but it's still
very good question. So let's see. I wish I could reproduce this figure, but you're saying something. Okay, so you have, this is my 0, this is my 1. I have a bunch of data points here, a bunch of data points here. And then you have this ripple, like ripple thing, and it goes like back up, down, like something like that. And then when you try to like threshold the 1/2, it's at one of these local, let's say, minima or maximum. Yeah. So what would happen here? Right. What would be the classifier here?
I understand the local minimum part, but for the maximum part, because they're kind of going down.
Maximum. Okay, so let me do another. So you want it to be at the local maximum. Ripple. Okay, like it's not going to be like, okay. Let's do like exaggerate here. Okay, the local maxima. Let's say this is 1/2. This is not 1/2. But okay, so what happens here? You're saying it's gonna like hit this at this point, and then go down and then back up. So that would be your classifier. So anything that's below this, yeah, maybe I'm gonna do it very. So that would be 1/2. Right. So anything that's above it, right, which is anything to this side, and still gonna be still fine, right? Are you trying to think about it? No, it could be. You're worried that like there is an interval in which. Yeah, okay, so let's see. It's fine. It's perfectly fine. So that would be your classifier. So the reason this is not supposed to necessarily be monotone. right? And it could be, how can we get what you want? Okay, so let's. It would be like this, I don't know. It's going to be hard to plot. But let's say, okay, this is like that. Then I would have something like this, right? I'm going to be below 1/2 here. Still below 1/2. And here is going to be above. It's like difficult to plot. And go back up, down, maybe. Okay, I have to do that. So this is above, right? So this is going to be classified as 1. This is below, this is going to be classified as 0. This is below, it's going to be classified as 0. This is above, it's going to be classified as 1. Right? This is perfectly fine. So this classifier would like be 0, jumps to 1, 0, and then jumps to 1. Right, that's fine. It could happen. It doesn't have to be monotone. So that's one of the issues with, like, if you have too many ripples, this is gonna, especially if it's near the decision boundary, then this could happen, and this is fine, right? In this case, it might not necessarily be good, but let's say if this interval is very small, your training error, so there are not that many points here, you can specify that, like, not too many nodes may be correct. But this could be what actually the classifier has to be, like, in the end, which one is the true one? So there is a true regression function, we don't know. Maybe it looks like this actually, we don't know. So for example, like in reality, we'll see, for example, logistic regression. What logistic regression cannot do in the usual case is, if my data is actually like this, 0 here, 1 here, and then back 0 here. So this is a perfectly fine classifier. If you do the Nadaria-Watson, like this kernel classifier, even if it's some ripples, it's gonna like be this and then go back up and then go back down. Right. So your classification would have this correct idea that in the middle would be 1, and in the here it's going to be 0, right? 0 here. So you can have these non-monotonic sort of cases as well. The regression function need not be like necessarily monotone. In this case, it was because it was linearly classified. So linear classification in the univariate or one-dimensional case would be exactly like this. So you have like a single point. Your decision boundary would have a single point to the left or to the one side would be like 1, the other side would be 0. This corresponds to the linear classification. And we also saw it like in the 2D plot. It was linearly classified in R2 as well. But need not have like linear class. We can have a situation like this, and we'll pick it up. So whether you're in this situation or maybe like in a monotone case where we have too many ripples, we don't know. Right. So it could happen. Yes. That's the point that I'm trying to make. So it seems like in this case, maybe this is too variable. You might say this is overfitting, maybe this is overfitting. It's a little bit hard to say here because this ripples don't change the decision boundary that much. You can see like it's pretty good here. Like it has a lot of ripples here, but we're not going to care about this classification. So that's why classification is sort of much easier than regression. I might be wrong outside the decision boundary, right? Whether the actual regression function here has to have these ripples or whether it's like smooth here, we don't know yet. Okay, but would you say this is overfitting? Maybe we'll talk about this. But in our case, one of the points of this is that it's not going to matter as much for classification. If as long as the ripples don't occur at the decision boundary. So here you're estimating the decision boundary pretty well. you're doing something like crazy outside the boundary. But as far as the classification goes, because the threshold, you're gonna be okay. Okay, this is one point of this plot. But this idea of overfitting or like bias variance trade-off, that's sort of what I'm trying to get at, hopefully in the next couple of lectures. You can say this is maybe underfitting, right? The ones that have like higher bias, lower variance, you can say they're underfitting. The ones that have higher variance and smaller bias, they might be overfitting. But the picture is like a little bit shady, more like harder, like easier maybe in the classification case, and we'll see that. So when I say variance, I want to point out that these ripples are not the variance. So the variance would be, so what is the variance of an estimator? How can I see the variance? So this is like a manifestation of the potential variance, but how do I actually, so this eta hat is going to be random, right? It's a random function, but randomness depends on the training data. How can I sort of have like an estimate of the variance of it? What should I do if I give you the data, how can you like design something to like measure the variance? But like what is intuitively the variance of eta hat? You can't read it based on a single plot. So if you're a frequentist, variance is a property of population. So you need to see many cases, right? How can we see the variance here if I want to? Anyone? What I need to do is to repeat this experiment like many times, get like this many, this is like about, I think, 398 training sample. So the total number of points that we have. I have to repeat this many times, and each time I form this eta hat, and at a given point, I can go and look at the variation. Right, so it's going to go in this point, it's going to be here or here or here, like there's going to be a little bit bar here, like a histogram, or like an error bar. Here is going to be an error bar, here is going to be an error bar. So that would be the variance as I make. So if you want to simulate it based on data, you can go subsample this, or like do a bootstrap kind of thing. Like, or if you knew the actual data, let's say I give you the bigger data set, because this has, I already split it. Let's say I have a bigger data set, you're going to go sample this many from it. Ideally, you want to sample from the population, but you don't have it in real data. You're going to sample this many samples once, twice, thrice, and so on. Each time you have one training data, you fit it. And so the variation across those samples is what constitute the variance. And the bias would be what is the mean across those samples, the expectation of, so the center of those. So we'll have a distribution here. The expectation of the center would be how far it is from the actual regression function. That would be the bias. And the variance would be how far, like the basically straight. So the bias would be, this quantity, the expectation of this minus the true regression function. And this expectation you have to take under the population. So under the variation in the training sample. So x1 up to xn. Every time I repeat the experiment, I'm going to get both x1 actually, y1 and 2xn, yn. So that would be the bias at that point. And the variance would be just the variance of eta hat x. At each point, we'll have a variance, right? And then there's going to be a trade-off between these two, as we'll see. So if I try to make this smaller, I can do it by increasing the bandwidth. I get things that are smoother. If you go and calculate, I think maybe there is a homework problem. You can repeat the experiment and then you can put error bars here. So how much variation? This would have smaller variation. Eventually, when h is very large, it's going to be very flat. They're close to being constant, so there's not much But you can see maybe like it's deviating from maybe the true regression, maybe the true regression function is here, but it's deviating more. So the center would be far from the true regression function. Maybe this, think of maybe this black one as the true regression function. It's not the true one, but they're probably close to the true one. If this is the true one, the center would be here, would be very far from this. The other one, the center, is like going to center around this, but it's going to be variable. At each point, it's going to be closer to the true one. So the bias would be smaller, but the variance would be higher. So maybe it's going to, the center would be here, but the variance would be like that. This one, the center is off, but the variance would be like that. So which one you pick is a bit of an trade-off. So we're going to talk about this, okay, for a while. Does that make sense? Bias variance. Have you seen bias variance? Okay, we'll see more of it, but that's sort of the essence. To see the bias and the variance, you can't see it from one single plot. You have to like sample from the population many times and do this experiment many times. Or if you can't sample from the population, which is what happens in real data, you have to simulate sampling from the population. You have to somehow do that. Okay. Subsampling your data would affect it because when I subsample, I change the variance, I change the information. So ideally, if you want to see the variance of your estimated for this sample size, you have to have this many sample size every time if you want to. In practice, we're going to have to subsample unless you do bootstrap, which is going to sample exactly this many with repetition. Okay, questions? Is this sort of clear? So we did start from a very basic principle and we got an estimator, which is pretty nice. And we can actually calculate the accuracy and we'll see like the ROC is pretty nice for this as well, like very high area under the care of ROC. So from first principles, we constructed a very simple estimator. There is no optimization involved, nothing, except setting this bandwidth. And so now let me ask you, let me show you another one. So this is for the box kernel, the kernel that has a x and x is 1 over h, that indicator, x minus x. So this was one of the proposals. K naught is basically indicator of u less than 1. And if you translate it and rescale by bandwidth, you would look like this. This was our proposal. One of the proposals was to measure the similarity. So this 1 over h is going to cancel out. It does this doesn't matter, as you have seen. So this is saying I'm going to like say that two examples are similar if the difference is in x is less than or equal to h. And this is what you can do it for this, and you get this. You can see the like the wiggliness is hard, like a much like sort of severe because this kernel is not continuous. So the Gaussian kernel is smooth, so the ripples are a little bit more tamer, let's say. But here, actually, the bandwidth also like this is not the exact correspondence. So the bandwidth here has a different meaning because there gets like squared. But in any case, you can see this again. This may be like overfitting. The black one may be okay. This one may be underfitting, but they're closer to each other. And you can see that at the boundary here is like there's not much difference. So it's really hard to tell or like care about the exact bandwidth here because the decision rule that you get from it is sort of similar. Okay, so you can play with this different kernel and you get different classifiers. But for the most part, they're going to behave similar. Okay. Again, this is the plot for the Gaussian case, for the Gaussian kernel. And this is the plot for the box kernel. Questions? So now, how should we pick the bandwidth? How can I choose between these bandwidths? That's basically the only training that I need to do to pin down the classifier. Once I have that, I have like the full specification of the classifier. I can go and classify like future data points. But I have to specify edge. How do you specify edge? Any suggestions? You go back to like the earliest things that we did, we set up a framework. There is something that we are after. Once you specify a criterion or like set a criteria for what is good, what is a good classifier, then you can like say, I'm going to pick H to have the best classifier. So we have to define best, but once you have it, then you can aim for it. So how do we define best so far? What are we after?
Minimum risk.
Minimum risk, yes, exactly. So we were looking at define the minimum risk classifier. And all this business is trying to estimate the optimal minimum risk classifier. And risk for us so far has been what? What is the risk that we consider? So the risk depends on the loss function. It's expected loss, and the loss could be different. So we have been focusing on a particular loss function, if you remember. What was that? The name of the loss function that we have been working with in the background. 0 something, 0, 1 loss. So what is the associated risk? Misclassification rate, maybe? Probability of misclassification. Remember so loss was indicator y hat not equal to y, and the risk was the expectation of the loss, y minus y hat. And so this would be the probability that y hat is not equal to y. Right? So that's misclassification, the probability that I misclassify it. This is going to be like, let's say, for example, f hat of x. So that's our goal. But do we have the risk? Can I calculate the risk for these guys? Do we have access to this quantity? If I have it, I can try to choose the one that has the smaller risk or the smallest risk, the smallest misclassification rate. Do I know it? Can I calculate it? The true risk. So remember we talked about types of errors, right? That business, what was that about? What do I need to be able to calculate this for a given classifier? So classifier here is like 1 if eta hat x is bigger than 1/2. Do I have the information needed to calculate this classification rate? Yes. The answer is no. Why? What do I need to be able to calculate this? Remember, we started from an oracle problem in which we knew something and then we could calculate this. What was the thing that we assumed we know, which we actually don't know in practice? The earliest lecture.
The distribution.
Yes, the what distribution? The joint distribution of y and x, right? Remember? So that we don't know. Like a generic x and generic y, they have a joint distribution that we don't know in general. In this case, it's hard because in the case where they're binary, we could specify with 4 numbers. Here, because x is continuous and y is binary, the joint distribution is more complicated. So you have to specify basically we'll see, like there are different ways, but you have to specify, for example, what is the distribution of x given y equals 0, what is the distribution of x given y equal 1, and also the probabilities of y being equal 0 and 1. If you remember that exponential exercise that you did, there we specified, for example, these distributions, and then you can calculate everything. But in practice, I don't know those. I either have to estimate them, but instead of estimating the distribution, we can try to estimate this. I don't have it because I don't know the actual distribution, but I can get an estimate of the risk, estimate of this classification rate. How do I get that? If you recall. How do we estimate the risk? Sorry? Training error. One way to do it is to calculate the training error, but we discussed that training error in general is not necessarily a good estimate of the risk, if you recall. Because
It's too low.
Yeah, most of the time, but there's a more there's a more clear objection, which is that depends on the training data. So the training error is used to calculate the classifier. Hence, the classifier depends on the training data, and then we are going to evaluate it on the same data. So there is dependence between the data that we're evaluating, the classifier, and the classifier itself. So, for example, we can't use the law of large number to conclude that the training error is consistent. But yes, you're right. In general, because we try to minimize training error, it's going to be small. So it's going to usually underestimate. What if someone asks you why it is not a good estimate, because it's in general not consistent, because of the dependence on the same data that we use to train the classifier. So what should we use instead? Test error. So that's what we did. So we calculate, like we get a better estimate if we use an independent sample. However, you obtain that independent sample. In this case, usually you split your data, right? You split your data into two pieces. You keep one piece independent of the rest. Assuming the rows are independent, you keep one piece aside, you train on one part, which would be your training data, and then you use your test data to test. So that gives you an unbiased and hopefully consistent, usually consistent estimate. Not usually, but sort of always consistent. If your training samples, like the test sample size goes to infinity. Okay, so that's what we can do. So I've actually kept a test set here. I can go and now I have my classifier, right? I have the classification rule here. I know eta hat, I know the exact classification rule. I'm going to plug in all the test data, the x's. For test data, I'm going to predict y or 0, that would be my y hat. So y hat I. So I'm going to have like x1 tilde, remember that was our notation. This is our test data. xm tilde, ym tilde. I'm going to go apply f hat to x tilde I, and this gives me y hat I. You can say tilde. I don't know how to write it, but let's not write it. So that will be my prediction for this test data. I compare it with the corresponding y, the actual y. And if it's not equal, I pay a price of 1, and then I average, or like sum them, divide by 1/m. So that would be my test error. I can calculate it. So apply the classifier to each one of the test example on the x coordinate, compare the result with the actual y, and pay a price of 1 if they're not, if I have a mismatch, and an average over the train. So this is the test set. Test set. We use this notation for it. So this is going to be our test of f hat. Okay. So I can do this, and this f hat would depend on, I could say, put an edge here if you want. So this depends on the bandwidth. So for each bandwidth, I get a different classification rule. So I get a different edge here, right? So you can see h equal 1 would give me one of these curves, and then that would be classification rule. H equal 3 would be another one. So this classifier is really, it's a function of edge. So I can say f hat of edge. So if I do it for every edge, or like for a grid of values of edge, So I can calculate R hat TE for a grid of values of H, the bandwidth, and then can plot, or actually you don't need to plot, but I'm going to plot this function H maps to R hat test error F hat H. So here I'm gonna have a bandwidth, and this is going to be the test error for F hat H. So I'm going to get a plot, and then I'm going to choose the edge that minimizes that function, right? The edge that for which I get a minimum has the smallest test error, so it's the best sort of. Hopefully, if the test error is close to actual risk, I'm going to be choosing the classifier among this class. So this defines a class of classifiers indexed by edge. I'm going to pick among this class a classifier that has the smallest estimated risk, okay, by choosing the one that minimizes the test error. Sounds good? So this idea is sort of called, what this is called. There are many different names for this. Like machine learning people will be saying like hyperparameter search or grid search. Like statisticians would generally call this cross-validation. Although cross-validation is like usually a slight variation of this, but I would say this falls within the general idea of cross-validation. It's not exactly cross-validation, but that's basically how you choose the bandwidth, how you choose these this is sometimes called hyperparameter. This model has a hyperparameter H, which we haven't specified. You have to specify, and so grid search, hyperparameter tuning, search or tuning. It's a form of class validation, although for cross validation, what people usually do, you just split multiple times and then you average. And oftentimes you train on one. So classical class validation, like split it into like, let's say, for example, 3 pieces. Okay. It's called threefold cross validation. You train, for example, on these two and then test on this part. Later, so that would be so this is what I described. So if you plot that, that would be good. But usually people repeat this. So the same as splits, but now I'm gonna train on these 2 pieces, and I'm gonna also test on this. And the next time I'm gonna like do train on these 2 pieces and then test on this part. So this is called threefold class validation. And then I'm going to average the test errors that I get. The reason why they do this is because they want to use each part of the data once in training and once in test, so that you have used all of the data. You don't need to do this. You can just do one. But this is sort of supposed to like reduce the variation. And so because this is going to be random and you're going to do that. So let's not worry too much about this. What I'm doing like here is this one version. The other way of doing class validation is just to randomly split. You don't have to split it into pre-specified forms. Like split it randomly at some point and do it multiple times. And each time you have a training and test, you repeat it and then you average. For us, what I'm doing here is just split once. One training, one test, I'm going to evaluate and test. And that's the part I'm going to do for simplicity. Okay, we're going to come back maybe later, discuss this a little bit more. But is this clear? So I have, for simplicity, split once, train on the training data. I have all these classifiers. Now I evaluate them on the test data. Then I'm going to plot this. So that's what you get. That's my bandwidth edge. This is R hat training F hat edge. So you get a nice plot usually. It's the same plot. This is the misclassification rate. So it goes from 0 to 1 here. I'm zooming out from the entire range. The other plot is like zooming in this one. So you can see there's usually like this nice dip So there's this behavior. So if H is very small, you can have higher Rasmus classification. If it's like too big, it's gonna be big. There's like an optimal value here. Near probably 0.25 or something, maybe. But anything here is pretty good, like close to 0.1, this classification rate. And the point of this is that even if you increase the bandwidth, it's not that severe. So you can see like in the grand scheme of things, this is not too much variation. It's not like going to 1. So even at that sort of large bandwidth, you're like having like close to 20%. The difference like 10%. It's a significant sort of, but you can this shows like the like moderate sensitivity of this classification rate to that overfitting business. As I mentioned, because the you care about the decision boundary, and decision boundary is like not that effective. So like from here to here, you have like a pay rate tiny price. So whether you go for 25% or 1, the difference is probably negligible. You remember this is just one test plot. If you repeat this, we did this before. So there's variation here. So difference between this and this might not be significant around it. So you repeat it many times, average, it would go away. But if I increase the test size, maybe it goes away. Maybe. But that's sort of the nice point. That's how you do parameter selection. Next time, we're going to come back and try to maybe see this in the context of regression. It's going to be more important. Okay, and we're going to like play with this bias variance trade-off more. Sounds good. Okay, thank you guys. I guess we're out of time. See you next time.